Welcome to ePathshala, the PG course for the computer science student. Today we are speaking about the ARM processor and the ARM instruction set in the embedded system course, okay, so which we are continuing from the past 2 weeks. We have already started with the ARM processor and we have spoken about the data processing instruction. In today's class, we are trying to aim to the remaining section of instruction set, which basically concentrates on the control instruction, the branches, and the data transfer instruction, the loads and stores. Okay. So, we are speaking about the two categories of instruction, the control instructions as well as the data transfer instruction. We have already spoken about the data processing. We are yet to speak about the interrupt based instruction, the program status register instruction and the coprocessor instruction. Okay, so speaking about the control instruction. So control instruction, as we all know, basically enables a course of execution to move from one point to the other point. So there could be a need in the necessity of a program where it needs to execute a certain section of code, a function or a procedure which is available at a different location. This could be basic necessity of a regular programming module itself, or it could be a basic necessity of some kind of interrupt which has been written at a particular different location. So, the interrupt service routine. So, for all these things we always need a branch instruction. So, branches which enables us to change the value, or maybe which can seamlessly change the value of the program counter, can move from one point of the memory location to the different point in the programming code section. So, if you look at branches, we have two categories of branches broadly speaking. One could be the conditional branches and the other could be the unconditional branches. Okay. With respect to the ARM processor, we have one shortcoming or maybe indifference that we normally think about with respect to the other processors. Normally when you speak about calling a procedure or calling a function, calling a subroutine, you always have a call instruction. Okay. Call instructions allows us to go to that particular function or subroutine, execute it, then it returns back with a return statement. Okay. Such call instructions are not available, or maybe they are not put into the instruction set of our ARM. So, that also has to be fulfilled by our branch instruction itself. So, we have two categories of branches in terms of which can imitate the call instruction. So, one is the branch that we all know, a ordinary branch which could be conditional or unconditional. The other one is the branch link, which basically tries to imitate the call instruction, which can go to the given location, target location, where the program counter could change to the new target address. And then when you want to return back, I have one more register which we have studied in the register classes, okay, which says like a link register. So, I need to take the return back address from the link register. So, I need to copy the link register into the program counter, so that I can come back and execute from where I had left. Okay. So, we have branch, branch link, BL. So, this is what is our BL, branch with link. And since we know that the ARM processor has two states, one is the ARM state, the other one is the thumb state. So, I may be executing codes or instructions that belong to the ARM instruction set, or the instruction that could be belonging to the thumb instruction set. So, in case if I am moving from one instruction set to the other instruction set, that is basically been done by the branch exchange. Again, the branch exchange could be with link or without link. So, just ordinary branch exchange which just basically moves from one set to the other set, saying that we are moving the state from ARM state to thumb state or thumb state to the ARM state. The other one which basically returns back after moving and executing a set of codes, whether it could be the thumb state, the thumb instruction, it returns back to the original callee location. Okay. So, that is the branch exchange. So, that is what has been shown in this particular table, like where it say like just branch PC is equal to label, it just moves to that particular location. When I say branch with link, PC is equal to label, then the link register which is normally having the address which has to be loaded into the PC when you have to return back. Then branch exchange basically speaks about one more additional parameter operand that we actually bring in over here, which gives the offset value to the program counter, and at the same time the least significant bit of this operand, which we are calling it as RM, the least significant bit of this can be utilized for setting the state of thumb, like thumb bit which we have in that CPSR, which can actually tell like whether we are working in the ARM state or in the thumb state. If this thumb bit is actually 0, it works in the arm state. The thumb bit is 1, it works in the thumb state. So, the thumb RM basically indicates that you are actually moving to the thumb state, provided this RM least significant bit happens to be 1. Okay. The same thing applies for the branch exchange with link. Okay. The only difference from the previous one to this one is basically the link register, which helps us to return back to the next location of the address, which from where I had left from the caller section. Okay. So, branch always, like any other data processing or data transfer instruction, can always be postfixed with conditions. So, conditions can be applied, which could be brought from our the bits that is available in the program status word. So, greater, lesser, all different categories of condition, which we had even seen in the data processing instruction. Okay. So, branch, if we look down to the syntax, so branch, whether it is whatever the branch link or branch exchange kind of scenario, it will always have a condition that will be post fixed along with the branch, followed by the label, the address to where we are trying to move. Okay. So, branch with link, the same thing, BL. So, branch link, the condition that we are trying to append, then the address label that I am trying to move. If I do not mention any condition, which normally defaultly means as always, that means I am branching it in a unconditional way, I do not need to check any kind of conditional flags. From where does this conditional flag comes? This conditional flag comes from these bits of our program status word register. So, the 28th to 31st bit of the CPSR basically supplies us the condition like carry flag, overflow flag, okay, the sign bit, all those things which can be utilized for the conditions for deciding whether the branch has to be taken or whether the branch has not to be taken. Okay. Then the branch link will basically be enabled by this link bit, the 24th bit, the link bit, which basically tells like whether I am trying to come back to the next address from where I had moved on, or whether I do not want to come back to that particular location. So, if you just look down, the offset value that we are actually speaking about with respect to the branch instruction. So, among the 32 bit of instruction, so 28 to 31, just as we had seen in the previous one, the 28 to 31 goes for the condition. Then these bits are for telling that these are branch instruction that we are working with, 1 bit for the link bit, the remaining 24 bit, okay, starting from 0 to the 23rd bit are the bit that will actually express our address where we are trying to move. This 24 bit can help us to scale, like search or move from the current point either in the forward direction or either in the backward direction. Okay. So, when you speak about the forward direction or the backward direction, the offset value for the program counter will be taken by that particular 24 bits. Okay. So, how does it take that particular offset value? It basically looks at that particular offset value, the 24 bits which we have, and to whatever the target that I need to go, it takes the difference from that to the offset of the, like basically with respect to the program counter. So, whenever we are trying to calculate the relative offset value, we will normally try to look in terms of the current program counter. So, generally when we are executing, let me say like instruction I, the program counter is expected to point to instruction I plus 1, the next instruction. Okay. Now, since we are actually working on a pipeline kind of scenario, the pipeline could actually fill in more number of instructions provided the different kind of stages that I have in the pipeline scenario. So, since we can have additional instruction that could also be creeping in and that has already started its execution scenario. So, we always take this target address minus 8. So, that we compensate for the additional steps that have been actually taken or the instruction that have been called for execution purpose. So, totally if you take this, you almost get 26 bits, and since we only have 24 bits of position to load that offset value, we will basically move this 26 bit 2 bit right side, 2 bit right side in the sense the last 2 bits generally are always assumed to be 0. So, I do not need to bother about the last 2 bits. Why it is always 0? Since we will always say like it is a word addressing that we are trying to do. So, word addressing in the sense in a given memory, okay, if I speak in terms of byte, it starts like 0, 1, 2, 3. So, the next address that I always speak will always be 4. So, if you look down for 4, the last 2 bits will always be 0. So, in that way the last 2 bits are generally 0. So, I can actually shift it 2 bits, ignoring that last 2 bits is always a 0. Now, this 23 bits which we are trying to speak over here rather than 23, 24 bits. 24 bits which we are trying to speak over here can give us a range of nearly a forward jump that I can do nearly of 32 megabytes, or a reverse jump that could be of 32 megabytes. So that is what is given over here, plus or minus 32 megabytes. Okay. So appending the condition with our branches, like any other instruction, we can even append the condition with respect to our branches. So the condition that we put over here, it's always a postfix. That is what is shown in this particular example, where it is actually deciding this branch not equal. So based on the condition that I have, that could be reflected on your flag because of the previous compare instruction. We know that compare instruction will reflect its changes on the status flags. So it will basically try to check branch not equal. Okay, so branch not equal, where we always speak about the equal scenario. Okay, so we can look into this different equality or greater than or lesser than kind of scenario which has been given in this particular table. Okay, like for example, if I don't give any condition, branch always, as we all know, like AL stands for like I am not branching any situation. Okay, so if you look in terms of branch equal, it's basically trying to look in terms of like when two comparison results in a 0. So branch equal, branch not equal, branch greater, branch lesser. So these are the list of different conditionals that I can actually append with respect to the branches over here. Okay. So branch link with exchange is exactly the same branch link which BL, then along with this branch link could be the condition. Then I need even a register which actually gives me the address which has to be loaded into my program counter. Okay, so the target, the branch target is generally specified by whom? It's specified by our RM, and the least bit in the RM is used to set our thumb bit, the thumb bit which is available in our CPSR. So bit 0 in RM can be put into the thumb bit, which makes it to either work in the arms mode or either work in the thumb bit, thumb state. Okay. So the processor, when it will switch to thumb bit, like when it will switch to thumb state, whenever the RM bit, the least significant bit of the RM bit happens to be 1. In case if the RM bit is 0, it actually retains itself into the ARM mode itself, or maybe it comes back to the ARM mode depending on what we are trying to do, from where we are trying to switch on from here. So branch link with exchanges generally will be used from moving from one state to the other state. Okay, so branch link with exchanges, if you just look down, is when we use this, whenever we want to move to the thumb subroutines. Okay, so when I want to move to the thumb subroutines, I'll put the target address over here and then assume where do like what does my RM bit says, based on which I'll actually look down to moving into the thumb bit. The link address, the return address that I normally try to put in the link register will be indicated by the L bit of our CPSR. So that L bit, the 24th bit, will actually tell me whether it's expecting the link address, the return address from the link registers or not. Okay. So that is a way we normally try to skip or move from one state to the other state. So these are some 4 examples that we have for the branches that we were actually speaking now. So branch unconditional, branch conditional, then this again is a branch with link that we were actually currently discussing over here. Branch label goes to the particular label address, then branch jump, okay, like a conditional jump goes along with the condition that we are trying to append over here, branch not equal. So if you just look down as subtract and append or update your flag. S basically says you need to update our flag over here. Okay, so this is a way that a conditional codes could be updated, the conditional flags could be updated, and that conditions can help us to switch on based on the different options that we actually provide to the branches or any other instructions. Okay, so these are the 2 examples with respect to the branch link and branch link exchanges, or the branch link along with the condition. So branch link less than or branch link greater or equal to. So it moves to 2 different locations for the subroutine 1 or subroutine 2, which we are trying to speak on over here. Okay. So initialization of address pointer. Now as we said, like we can actually point to a particular location in the memory. So that could be done by one instruction which is basically called as a pseudo instruction, which is generally named as ADR. So the ADR that we are actually trying to speak over here basically has one option of pointing to a location in the memory which normally could hold some series of data or array of data over here. A array of data could be pointed by this particular ADR. So that is what your example here shows, like we have two tables, table 1 and table 2. So when I say ADR R2 table 2, basically my R2 register is pointing to that particular table 2 where I have some series of data over here. So address pointer, it works like an address pointer. Now after branches we will try to speak about the data transfer instruction. Data transfer instruction, if you look in terms of the data transfer instruction, when we speak about data transfer, how many bytes are we trying to transfer, or maybe how many words are we trying to transfer, that will actually tell like whether it is a single register transfer or whether it is a multi-register transfer. Again, there is one more kind of transfer that we will normally try to speak over here, which is a swap. Swap in the sense we are exchanging the values, okay. It could be exchanging a content from the memory with respect to the register. Then again in turn like copying back the content of the register into the memory. So that is what the swap normally tends to mean with respect to most of our implementation. So we can have a single register, multiple register, that means a block of data. We are trying to copy a chunk of data maybe from the memory towards the register, or I am trying to store a chunk of data from the register which is available, a series of register that we are trying to speak R0, R1, R2, R3, copy that, store that into the memory location. So multiple data. So that could be done either with respect to the copy block, like which we will actually look down, or we can even think about this moving of values using a stack implementation also. So single byte or multiple register movement. So single register data transfer, when I say single register, there is only one register which is involved in this load or storing. So when I say only one register, the storing or loading process could be either in terms of the byte or either it in terms of the half word or either in terms of the word. So that is what is this examples of storing. When I say just LDR, STR, it is basically with respect to load and store for a word purpose. The same LDR with B or H basically means B stands for byte, H stands for half word, okay. So the load can also be loading a signed representation. For example, I have a byte in my memory which is a signed representation. So when I speak about a signed representation, the most significant bit happens to be the sign bit. So if I am trying to load that particular content of that memory into my register, which is generally happens to be a 32-bit kind of register, then the sign bit has to be extended. So that has to be done when I speak about a loading a signed value. So whether I am loading a signed byte or whether I am loading a signed half word. In a loading a signed word, you do not have big confusion over there, because the sign bit exactly copies to the most significant bit, there is no kind of extension needed. Whereas when I am loading these two like byte or a half word, the extension is actually needed over here. So we have load. Again, load can also be appended with conditional, just like most of our instruction does. Now when you speak about all this instruction, there are few addressing modes that actually comes into picture. So which normally comes in most of our computer architecture kind of scenario. So register indirect addressing mode, then we speak about base offset addressing mode, which again has a base register or a offset content which could be provided to that particular base register either as an immediate value or either as a register value, okay, or either as a scaled value. Scaled value in the sense I could do some kind of shifting operation to find out what I am trying to add to that particular base register, okay. So the other addressing mode which actually does a chunk of copying kind of thing is basically a the block of copy that we are trying to speak about. Then the other usual data structure that is normally available with most of our implementation is our stack addressing mode. So this is an example of register indirect which we all know. So where I say like I am trying to load the R0 with the address pointed by R1. The same scenario happens with respect to our storing process. So this is an example of a diagram which represents with respect to the register indirect, where you look down, if you just see here, we are trying to get the address from the R1 register, the load instruction, which is trying to load the content into the R0 register. So R1 register has pointed to the address of 200, so go to 200, copy whatever you have, put it inside your R0, okay. So this is what is our register indirect, which can be even thought of for the storing purpose. Then again, when you speak about the index mode or the offset value that you are trying to add, we can have a pre-indexing for the offset addressing, or a post-indexing, or a auto-indexing. Pre-indexing, the base index mode that we are trying to speak about over here, is generally like first find out the effective address and then copy the content or store the content. That is what is been shown over here. Like when I say LDR R0 R1 hash 4. So this is the offset value which I need to add to the base address R1, then go to the memory address which is pointed by R1 plus 4, copy the content to R0. Post indexing, do the addition or find the effective address after copying the content from the base register pointed value. So that is what has been done over here. R1 points to some location, copy that content to R0, then update your R1 with respect to that offset value that I am trying to speak. So just the difference is like the square bracket. If the offset value is within the square bracket, it is basically pre-indexing. If the offset value is outside the square bracket, it is basically our post-indexing. So we are not showing the example of STR, which is kind of similar to what we look into the LDRs over here. Auto-indexing, basically has this one more additional exclamatory mark that we actually put over here. So what does auto indexing tells? Okay, you have the base address and the offset which gives you the effective address, copy it to the R0 and ensure that this R1 is basically updated with the new address. We are overwriting the new address into this particular R1, so that generally the looping process which actually keeps on pointing to a memory location and then keeps on incrementing itself so that it points to the next location. The increment instruction, a separate increment instruction is not needed, which is normally done by this overwriting of our base register with this offset value, okay, which almost saves most of our cycle time, in turn saves our energy, in terms which makes it more effective and faster. So this is a diagram which is with respect to the pre-indexing kind of scenario. You can just look down over here where it says like the R1 which has the address of 200, the offset is 12. So first I need to add, get the effective address and then store condition, store the content into the effective address. So 200 plus 12, 12 basically stands as C, so 20C. So store the content of R0 which is 5 into the effective address location. There could be some variation in with which I can actually write this instruction, that is what is actually been shown down over here. We can just look it out later on and move on to the next thing. Post indexing, same similar kind of scenario. The only difference is we write the address into R1, the effective address into R1 only after copying or storing the content. So the initial pointed address of 200 is where I try to store the R0 value. So previously I used to store it in 20C, now it actually stores this 5 in 200, okay, or 200 kind of thing. Okay. The multiple data transfer basically as we said, like copies a chunk of data, okay, copy is a chunk of data in the sense the same LDR or STR basically is indicated as LDM and STM, that we are trying to access a chunk of multiple data. So when I copy a chunk of multiple data, what is the order it tries to do when you copy? So it could do it in any order, but generally how does it copy is like if I say like if I am starting from the address 200, I am going until 209 something. So the lowest address value is actually put into the register which is of smaller number. For example, if I have register R0, R1 and R2, R3, the address content of 200 will be actually copied to R0, 201 will be actually copied to R1. That is the way it actually tries to do when I mention a series of register. So we can just look down over here, we can go to this example that we have for your multiple data transfer. So it basically copies a chunks of data. It can have all the different addressing mode that we had actually spoken until now, all the auto indexing, post indexing, everything. So this multiple chunks of data which I am trying to speak, which keeps on moving across the array of memory that we are trying to copy from or write into. So this array could be again done in a post way, post indexing way or a pre-indexing way. So that is what is this increment after or increment before or decrement after or decrement before kind of indicates with respect to our STM or LDM. Okay. So, a small example that we can actually look down over here is this LDM IA, like load multiple data and increment after. So, what are we trying to load over here? We are trying to load these 3 register R0, R2, R5. So, from where we are trying to load? We are trying to load it from the address that is actually pointed by R1. So, R1 could be pointing to some address, let me assume it to be 200. So, basically the address 200 content will be copied to R0 because it is the smallest register. The next R1 plus 4, because we are actually moving word by word, each register is of 32 bit. So, the next content will be copied to R2, the simultaneous consecutive content will be copied to R5. This is the way it actually goes on. So, this is what is our block copy kind of scenario. So, the block copy which is actually speaking about this load or the store of multiple datas, which could be immediate increment after or increment before kind of scenario. A small example where we can actually copy, in the previous example we had only 3 register which was actually copying. In this scenario we have a series of register like starting from R0 to R11. So, each register 32 bit, 32 into 12. So, we almost end up having 48 bytes over here. Okay. So, the next addressing mode is the stack addressing mode. Stack addressing mode, we will just look down to this small example that we have over here. So, stack again increment after or increment before has 2 ways, like whether I am trying to go in a ascending way or whether I am going in a descending way. So, full empty. So, whether I am trying to point to a location which is having a data or which is empty with a data, which does not have a data. So, full ascending or empty ascending, full descending, empty descending. So, all these how they are implemented? They are implemented using this increment after, increment before kind of scenario. So, 4 examples of stack which actually shows like increment after over here, which just if you look down, we are starting from the address of 100C. So, basically if I say increment after, if I have to push a value there, store a value, STM basically store. So, I will store the content of R0 and then increment after to the next location of, let me say 100 after C, 100D. Then again I will store this, go on. So, this is the way the other diagrams which imitates increment before and decrement after and decrement before. Then coming to the swap instruction, as we said, swap instruction exchanges data. So, if you just look down, this is the general syntax which also could be appended with conditions. So, if you just look down, this is the memory that I am trying to point. So, this content from the memory Rn will be copied to the destination register Rd. Then the content from Rm should be put into the Rn, swapping. So, in case if I want 2 register to exchange themselves, then maybe I can put Rd itself, so that in case it literally means it is a true exchange between 2 A and B. B's copy goes to A, A's copy goes to B. So, generally where do we use it? We use it for the mutual exclusion purpose when we speak about the swap. Okay, so, a small example over here, and this is a diagrammatic representation of that particular swap kind of scenario, which shows like how the content of R and Rm gets copied in turn to each other. And why do we use swap? It is an atomic operation. So, I do not stop in between until I finish off this copying business. So, that is the reason it actually finds itself with respect to the semaphore kind of implementation, where I try to find the mutual exclusion using the property of swap instruction. So, what have we looked today? As we conclude, we have looked through all the choices of control flow instruction that we have, and we have looked through all the data transfer which has been done by the load and store instruction, and we even looked through the different addressing mode, the register addressing mode, the index addressing mode and the stack addressing mode. So, these are the references. So, as of now we will conclude and move to the next chapter. Thank you.